Hi my friends, in 2016 I posted this mechanism on grabcad.com. What governor? As you can see, the rotational motion produces a centrifugal force that causes the clogs to come in contact with the drum and control the rotational speed while keeping it constant. A similar mechanism is this centrifugal governor, which we already know now. It has a grounded housing and some mobile parts. In transparency are the parts which are rotating only. In red are parts which also rotate, but they have either rotation about this axis and translation on the vertical beside rotation of the bushing. I want you to know that I have worked hard on this mechanism to be as expressive as possible without going into too advanced technical details, so that also beginners to understand what is this about. We'll recreate this mechanism, but now in a way to be compatible with dynamic simulation. Let's start. We create an assembly, yes, by placing first the half housing placed grounded at origin, and as we did in the previous tutorial, we rotate to be visible inside. We select Set Current View as Home, Fit to View, to have this permanent position when we use Home. Okay. And then we place also other parts, cross shaft, ball bearings, and limiter. Okay, we constrain them. You see, to use place we have the shortcut P from Papa, and to constrain we have the shortcut C from Charlie. Yes, when I say Papa or Charlie, you know what I do. Charlie for applying insert to place this ball bearing inside the housing. Apply. Then the other ball bearing to the cross shaft. And the cross shaft with the ball bearing on the housing. Now we have the same constraint of the limiter to this circle. Okay, F6. Now we see that this is the only movement, but we want to move also the ball bearing together with the cross shaft. To do this, we apply constraint Charlie between the plane XY of the cross shaft and the plane XZ of the bottom ball bearing. Apply. Then the same XY plane with the XZ plane for the other ball bearing. Okay, now when we rotate the cross shaft, the ball bearing is also rotating. What means this? This means that this part made of two rings and the balls, which are only one part I told you about. Well, this part is rotating inside the housing. Yes? But if we don't apply here a friction, yes, between these two, it doesn't matter what the interface is where that rotation takes place. Yes? We open the dynamic simulation module and we apply gravity. Double click. We select the value of gravitational acceleration and place it with minus on the Y axis. Yes? Okay. To hide this vector, we click on the name. By the way, let's save the assembly as centrifugal regulator dynamic simulation. Save. Okay. Now we use the shortcuts Papa and Charlie to activate the synonym dialog boxes that, as you can see, does not appear here on the ribbon. Papa, the nut. 1, 2, 3, 4, 5, 6, 7, 8 nuts. Escape. You see them here. Yes, all of them. Now, Charlie, for constraint, with this solution, to place the first or a random nut, say here. If I close this, okay, we see a change in the browser. We see that standard joints appeared and there are two components, a grounded one, which is the housing, and the mobile group or groups, which are composed from welded group. They are considered welded. The cross shaft, yes, this part is welded with the ball bearings, with the limiter and with the first nut, this one. The other one are not mentioned here. What about the standard joints? Standard joints is only one, revolution. We can rotate this and you see the free rotation of the cross shaft. We continue with the other Charlie. Charlie aligned for this, placed here. Apply. Charlie for this, apply. Constrain for the next here. Okay, now I make something interesting. I make this not visible. I can use the shortcut Alt V. For the housing, we know where it is. It is there. It is not lost, but we don't see it. We rotate the cross shaft and Charlie again. Same Charlie. Apply. Apply. You know the procedure because I hope you created the assembly. Okay, now Papa for axles 1, 2, 3, 4. Constrain, same solution. The first one here, the next one here, the other one here, and the last and the last and the last hole, which is this one. Okay, F6. Let's save again. Okay, because now we want to place the counterweights. P or Papa for counterweights 1, 2, 3, 4. Charlie, this comes here. Apply. This is placed here. Apply. This one is placed here. Apply. And the last one is here. Okay. Good. Now let's see what happens if we activate the play of the simulation player. You see, in 1 second the gravitation make that counterweights to balance. Okay, save it. We have a first result. Now I change this with 5 seconds because we want to have a longer time to apply other imposed motions. You have to be very careful because now I tell you about new things. We go to standard joints, we select the cross shaft, which is in a welded group, and half housing. No other is a joint between half housing than this welded group 3. The welded group 3 is this one, which of course contains the cross shaft. Good. We go to this joint, revolution, and apply properties. this has only 1 degree of freedom rotation. We select it and we go to imposed motion. We activate it, and from here we have 2 possibilities: to create an input grapher or to apply a constant value. But before this, I want to make something with the units. You see, we have here the simulation settings, a very important tool which has to have enabled the first option: automatically convert constraints to standard joints. These standard joints appear automatically when we place the first nut in the environment dynamic simulation, as you saw. The constraints are transformed into joints because joint is the name in the dynamic simulation and constraint in the assembly. And the other setting is in the more: input angular velocity in revolutions per minute, RPM. We prefer this unit instead of degrees per second because we are familiar with this unit. Okay, now we go back to the half housing joint to apply a constant value in RPM, not in degrees per millimeter, of 50 rotations per minute. Okay, now if we start, you see some vectors here. We can eliminate them by clicking on the name of the assembly. We start rotation and you see what we have. Go back, construction mode, to change this property with the other input grapher. Input grapher means to select a low of rotation. We are limited in 5 seconds. 1, 2, 3, 4, 5. Now is 0, and we have to select other positions. I move this point up, and you see this is the first moment in our 5 seconds range of time. This point has coordinates x1, y1, and the other point x2, y2. The first one is 0, 0. The other one we want to be placed at 1 second and to have the value of 100. From 0 to 100 is the first. I rotate the wheel of the mouse to see better this graphic. I add another point. In this point, right click, add point, and now we have another segment, yes, from 1 to 3. We start from 1 second and 100 rotations per minute and ends with 3 seconds and also 100 rotation per minute. I use the wheel again to place here another point at the second 4. We want to come back to the 0. Yes, 0 must be here. So we have this graph. Yes, from 0 to 1 second is acceleration. From 3 seconds to 4 is deceleration. Yes? Okay, you understand this. We have a time of 5 seconds and we select how to be this cross shaft rotates. Okay, okay. And now we click again here. We start the rotation. You see, at the second 4, the rotation stops, but these counterweights are still balancing. We go back, we apply construction mode, and we save the mechanism in this condition. Then we finish dynamic simulation because we want to see again the half housing visibility, to add some other components. One is the bushing. Place the bushing here and make it coaxial with the cross shaft. Okay, I move it here somewhere and I place some other parts special created for you. Place the ruler support. We have a ruler here to be constrained as insert on this circle with this circle. Apply. The other two objects to be added are the ruler, which is this, and the ground zero here. We constrain this ground zero inserted on the ruler support. Apply, and we make this not visible to see inside because we want to apply now insert to this circle on the bushing here. Apply. As you can see, this ruler has some notation here. We can rotate it to place in a better position, and now to make it parallel this solution, this face with the face of the housing. Apply. And also we rotate this. This is not movable on vertical because it is constrained to the support, which is not visible, but it is taken in consideration. And we make the constraint between the back of the channel and the face of the ruler. OK, F6. Now I think that this is better placed so I go back to the ruler, I double click the angle and I change the value in 135. Not good. Minus 45. This is, yes, good. You see here very well this ruler. Now we can move it together with the bushing, but we cannot rotate the bushing. I place this somewhere here outside of the ball bearing, and now I make not visible this, the ball bearing, the other ball bearing. You'll see why. And I go now to the dynamic simulation. But before, let me rotate this up, this counterweights up, to have a better possibility to constrain this cylindrical faces with the bushing. But this is to be done in the dynamic simulation module. Environment, dynamic simulation, and we insert joints for placing these cylindrical faces on the planes, not with tangent in the assembly, but with joint in dynamic simulation. The solution is sliding cylinder on plane, not rotating this, but moving it on a plane. You see, we have to select first a plane and then a cylinder. Well, the plane is this, and the cylinder is this. Apply. Now when we rotate the counterweight, you see they are moving together. Then the other face, cylinder, apply. Another face, another cylinder, apply. And the last is this with the cylinder. Okay. Now we can start the rotation to see what happens. Okay? Are you ready? Let's start. As you can see, the movement is not uniform because the processor has to collect a large amount of data. When we repeat the action, as you will see, the movements will be uniform because the collected data are used immediately. Look now. See? Okay. And now I want to make something. I want to see inside. If we apply visibility, we don't see the objects. So we use view, 3/4 section view, and we select two planes, this one and this one. Okay, now we see inside. You see, if I rotate the cross shaft, you see all the movement. Why I want to do this? We go back to the dynamic simulation and we apply again the movement, the rotation. All is respected here. This is tangent, okay, but the movement is not what we want. Okay, and what do we want? Well, we want to put this toroidal surface in the counterweight gap. To make this, we have to add another joint. The joint is 3D contact, and we have to select two components which we expect to come in collision. This part with toroidal face is one, and the other is the counterweight, as you can see. Okay. We are sure now that the two faces of the counterweight are obliged to maintain the toroidal surface between them. Let's see. Once again. You see? They are not getting outside this space. This is very important for us to have limits of this movement. The action is slower than before because the processor must solve all the time this collision between parts. We wait for saving data. And we go back. However, we want to respect the original design, this design, and place a compression spring instead of restricting this movement between the two faces of the counterweight. So we suppress this last force joint, suppress, and we know what happens here. Let's place a spring between these two faces. What faces? This one and the other one. One is the cross shaft and the other is the bushing. Let me rotate this a little to see the cut. Yes, this is placed in a cut, and to move up the bushing, so to see correctly the position of the cylindrical face. Now to add a compression spring in dynamic simulation, we create another joint which is spring damper jack between that two points, component 1, component 2, point. The point is this one. The circle has a center, the center is a point, and the other one is this one. Apply. Now we see a compression spring. Good. Let's apply right properties to this object. Firstly, we know that this dimension from here to here is about 75. This is the free length of the spring. The real is more than 75. Let's apply 92. Let's apply a stiffness. Let's apply a damping because there are some frictions there. 5. The diameters here are 30 inside, 44 outside. This means that 37 is in the mid. I place here the value of 37. Ten is the value of facets, the maximum. Turns are 8. Wire radius is 3. Oh, this must be radius, not diameter. So I place 37 divided by 2. Okay, this is the real compression spring. Okay, and now we apply a simulation. Oh, as you can see, it's almost okay. The spring is oversized. Now waiting for simulation to end and the data to be saved. we'll change dimensions of the spring to be not so great. Okay, we go back, construction mode, and we edit the properties. Free length is too great, 82 is a proper value. Let's see again what happens. As you know, we have to make a calculus here, but we try so in several attempts to find the real value. Looking to the situation, this is why we use dynamic simulation. Now is good. You see, taking a look to the situation, we appreciate that the spring must be stronger than it is now. But this is the detail. Let's see to the big picture, which is more interesting. We go back, yes, we let Inventor to collect all the data, and now F6, yes, we know now what happens below here. Let's see what happens here, but we don't see very well, so I get out, I apply view and end section view. Good. I also make visible the housing, visibility, and the ruler support, visibility, and the two ball bearings to have a good image of what happens here. Yes. And now we go back to the dynamic simulation and we apply again the run. You see here better what happens. The movement is near the 0. I made this by studying the situation, and once again we see that it is placed in the good position. The range of movement is still very little. The length to be 85. Okay. Start. Now is better. Once again. Yes, this is a good position. If not, you can make other trials to see how it must be. The interesting thing is that even if here we have a spring, we know this, yes? You see, the spring is not visible at all. I create a new view, half section view for you to see better the situation. Now you see that compression spring and all the situation. Yes. Okay. But when we finish dynamic simulation, no any compression spring is here. Oh, but we want to place here a real compression spring. Now I make not visible the ball bearing to see inside. I made not visible the bushing. Where is the bushing? Here. Visibility. Now it is visible. And we use the design to create a compression spring. Now we know something about this compression spring, the one we want to use. So we select the axis. This is the axis. We select the start plane. This is the start plane, and we place here the data. 85 was here. Wire is 6, yes. The diameter outside is 41, okay. The number of turns is 6. Active coils, yes, active coils is less than all the coils. And we go to calculation, where we place some loads. 50 kilogram force is good for minimum load, or maximum load 100 kilogram force, and working load is 50. Okay, this seems to be good. Maybe this is too high. Let's place here 35 kilogram force. And now calculate. Calculation indicates design compliance. Okay. Okay. And now we have the real compression spring in its position. And when we use dynamic simulation, we use the other. Look here. The other compression spring, yes? The one which is animated by the dynamic simulation. You know what I say. Well, I think that you learn something from my project and realize that the third part of mechanics, dynamics, can be covered by dynamic simulation in the Inventor. If I ask you directly, I think you can tell me what the first two parts of mechanics are. If not, then I tell you. They are statics and kinematics, right? That's all for today, my friends. Thanks for watching. Bye-bye.